So today we're going to be looking at building a simple power supply, and the first step in that is we have to take the electricity as it comes in on our mains or from the wall, which here in North America is 120 volts AC, and eventually we're going to have to turn that into something small, like say 5 volts DC. And there's a bunch of things we have to do before we can get there. And the first step is we have to take the 120 volts AC and step it down to something, a little more easier to manage and safer. So that's what this device here will do. This is a transformer, and electrically it's an extremely simple device. It's an iron core, and around that iron core there's a bunch of wire wrapped around, and there's 2 coils wrapped around. One coil we call the primary, and one coil we call the secondary. And so in the case of this transformer, which is designed as a step-down transformer, 120 volts goes in here, and 12 volts comes out here. Now it's AC on both sides, so there's still more things we'll have to do, but this will take our much higher voltage and turn it into a much lower voltage. And it's devices like this is why we use AC electricity to transmit electricity all over the place, because in order to transmit it, we have to increase it to a high voltage to reduce loss on the line. And these are very simple devices, so it's very easy to convert, but they only work with AC. So they can convert, use a big transformer, which a big chunk of iron with some wire wrapped around it, to take the electricity as it's made at the power plant, boost it up to several tens to 100,000s of volts, ship it to our city. Then they have more transformers which step it down to a lower level until it gets to our house at 120 volts. So we're going to use one of these guys to step down our electricity for us. So let's take a look at, we're going to start looking at our transformers here. Now what we're going to do is we're going to use this doorbell transformer is going to be our AC source, partially because it has 3 voltages available on it, but also it's current limited. So we have mains voltage coming on this side, but it's limited to the amount of voltage and current that comes out of this side, which makes things a lot safer. On this side, the current is limited by the circuit breaker at 15 amps at 120 volts, and that's kind of dangerous. But on this side, it's down to less than an amp, and roughly 8 to about 20 volts. So much safer. Now, the first thing we're going to do is we're going to look at various aspects of AC, measuring AC electricity. Now here I have one of my multimeters, and here it says true RMS, and what that means is true root mean square. That's important for measuring AC voltage. So if I put this on AC volts, and then I can hook it up to the transformer here, we say that it's giving us about 10.4 volts AC. And it doesn't matter which way I put the probes in, because AC goes both ways. It's still 10.4 volts AC. Where the RMS comes in is the way it's measuring the AC voltage. And to see why that makes a difference, we'll bring in the oscilloscope. And I have the oscilloscope set up to do some measurement. So here we're going to see what the maximum voltage is. We're going to see the frequency, the peak voltage, and the root mean square voltage. So let's hook this up to our transformer here. And I'll take this probe with this bit off, and then we'll just plug this in here. And there is our AC coming from the wall. It's dropped through the transformer, and we can see here that the RMS is indeed 10.4 volts. However, the voltage from here to here is not that. If we go, I've left channel 2 on at 0 volts here, so we can see where 0 volts is. So if we go from 0 volts to full positive, that's about 15 volts. And peak voltage from here to here is about 30 volts. Root mean square is somewhere down a little lower, and that's kind of where the effective voltage is. And that's what your most volt meters and multimeters will report, that RMS value. And that's the effective voltage. And that's because AC, of course, is moving up and down. So at any given moment, it may be at 0 volts, it may be at 3 volts, it may be at something else. So when you're measuring AC voltage, that's one of the things that you have to remember, is that they're giving you the root mean square voltage. So what I've done now is I've hooked up our step-down transformer up to our AC source, and we can see that at this end we have, going into the transformer, we have AC. If I can get that to stay on the thing there we go, we have AC and at 10.3 volts. And if we come out here to the output, we have much less AC. So let's turn this up. Oops, go on channel 1. Down to 2 volts there. And then we definitely are getting AC out as well, but just at a much lower voltage. Let's do that. Turn measurement back on, and then there we go. Now we're getting only 1.24 volts. So 10 volts is going in, 10.4 is going in, 1.2 is coming out. So basically this is dividing by 10. So whatever comes on this side in AC, and it is coming out as AC, which is why we have that there. So whatever's coming on this side gets dropped by about 10 to come out on this side. So why don't we take the oscilloscope out of the way. And we can bring in our multimeter, and we can see that it also tells us the same thing. So we have 10.4 volts coming in, and 1.2 volts coming in there. And so this is just basically taking this voltage and dropping it down to that smaller voltage, basically dividing by 10, because this is nominally supposed to be 120 and this is supposed to be about 12. So this is acting as a step-down transform, taking a low voltage, making it a high voltage. So this transformer we've been using is a standard transformer that basically takes a voltage in 2 wires in one end and gives out a lower, in this case a lower voltage on these 2 wires here. And this is called a regular or end-tapped transformer. So that means that these 2 wires come off on the end of it. So basically we get a voltage coming in here getting transformed into a single voltage on this side. Now sometimes you want more than one voltage, and they make transformers for that as well. That's where this guy comes in. This is a center tapped transformer. So we still have our 2 inputs to our primary coil here, but we now have 3 wires coming out here. These 2 are end tapped, so they go. This is one end of the secondary coil. This is the other end, and this is the other end. But this guy is in the middle of it. So halfway through, they stuck this guy in, attached it to the secondary coil, and then they kept winding and then wound this guy in. So this is a center tap transformer, and it has some interesting properties as well. So I've hooked up our center tap transformer to our door rail transformer here, and into our primary coils, we're putting our 10-ish volts, and coming out on our secondary coil, on the end taps, we're getting about 1.3 volts, so almost a divide by 10. But here, if I go to the center tap, I only get about 0.6 of a volt. So I'm getting about half of what I got here. And so this allows me to get 2 voltages out of here, because I can get the full voltage out of this and then half the voltage out of, say, this or this, because this will be the same on both sides in terms of how much voltage there is. So again, we can take a look at that. This with the oscilloscope. Bring the oscilloscope in, like so. And this time we have both probes. And we just take channel 1 for now. We can take a look and see that indeed, whoop, we have to change that there. We are getting our 10 volts that we got before. Now if we come to this side, we'll chat that down to 1 volt, and we'll attach this to here, and then we will attach this one to here. And here we're getting our 1.33 volts. Let's get the trigger stabilized a little bit. There we go. So we've got our 1.33 volts. And then if we move, say, this over to our center tap, we now have our about 0.6 volts. Now what's interesting with this, if we bring in our second channel here, so we'll do channel 2, and we'll make that down to 1 volt as well. So, and I hook it up the same way. So I put this on the center, the ground lead on the center tap, and I bring the other lead over here. We can see that now they're out of phase. So I'm just going to move channel 2 down a little bit. So if I use this as my ground, because you can see that this is my ground, this is the ground lead on the oscilloscope probe, that my 2 channels are now out of phase. So that's an interesting property of these transformers. If I simply come back, and I can just touch that like that, they're still out of phase. If I bring it in and touch here, I'm not getting anything, because that's what it thinks is ground. So, and this way we'll actually short things out, because now ground is going to be in 2 places and the oscilloscope will wonder what's going on. So I'm not going to do that. So if you're using the center tap, you actually can get a different wave on both sides and half the voltage, and over the top, and get the full voltage across the top.